They lied to you. Not intentionally, but they did. Every scientist, every documentary, every article for the past 13 years told you Andromeda would collide with our galaxy. Now, they're admitting they might have been completely wrong. Today, we will see the new data from our most powerful space telescopes revealing something that shook the astronomical community to its core, the collision we've been certain about for 13 years. It might not happen at all. And here is a question for you. What's the first question you'd ask an alien civilization if we made contact with them tomorrow? Let me know in the comments. I'll pin the most creative answer. Now let's begin. In 1912, astronomer Vesto Slipher made a puzzling discovery. He was studying the light from Andromeda when he noticed something strange. The light was shifted toward the blue end of the spectrum. You've probably heard of redshift, where light from objects moving away from us stretches out and becomes redder. Well, this was the opposite. A blue shift meant one thing. Andromeda wasn't moving away from us like most galaxies in the expanding universe. It was coming straight at us. For decades, scientists debated what this meant. Was it really heading for a collision, or would it pass us by? Then in 2012, everything changed. NASA's Hubble Space Telescope, working at the absolute limit of its capabilities, measured something that had never been measured before: the sideways motion of Andromeda across the sky. This is incredibly difficult to do. Imagine trying to watch a distant airplane and measure how much it's drifting left or right, not just whether it's coming closer. Now imagine that airplane is 2.5 million light-years away. That's what Hubble pulled off. The verdict seemed clear. Andromeda wasn't just approaching us, it was heading straight for us. The collision would happen in roughly 4 billion years. Our beautiful spiral galaxy, with its elegant arms wrapped around a glowing core, would be destroyed. Andromeda, even larger and more massive, would be torn apart as well. The two would dance through each other in a cosmic ballet of destruction, their stars scattered, their shapes distorted beyond recognition. Eventually, they'd merge into something entirely different, a giant elliptical galaxy, a spherical blob of stars with no spiral structure at all. Scientists even gave this future galaxy a name: Milkomeda. The prediction became scientific gospel. It appeared in every astronomy textbook, every planetarium show, every documentary about the fate of the universe. Computer simulations showed us exactly what it would look like. First contact in 3 billion years, with the galaxies starting to distort each other. Full collision in 4.5 billion years, with stellar streams being ripped across space. Final merger in 6 billion years, with a new elliptical galaxy taking shape. The timeline was clear, the outcome was certain, or so we thought. Throughout the 2010s, astronomers continued studying the local group. That's what we call our little corner of the universe, the Milky Way, Andromeda, and about 60 smaller dwarf galaxies all bound together by gravity. They refined their measurements, they built better simulations, they factored in more variables, and the prediction held. A collision wasn't just likely, it was virtually guaranteed. But here's where the story gets interesting, and where we need to talk about how science actually works. See, every measurement in astronomy comes with uncertainty. When Hubble measured Andromeda's sideways motion, it wasn't a perfect measurement, it couldn't be. These are the most difficult observations you can make. The uncertainty was relatively small, but it was there. And in science, small uncertainties can sometimes lead to big surprises. Enter the European Space Agency's Gaia spacecraft. Launched in 2013, Gaia has one job: to map the positions and motions of stars with unprecedented precision. It's created the most detailed three-dimensional map of our galaxy ever made, tracking the positions and velocities of nearly 2 billion stars. By 2020, Gaia had collected enough data to revolutionize our understanding of galactic dynamics. At the same time, astronomers were making better measurements of something else: the masses of the smaller galaxies in our local group. This might not sound important, but it's crucial. You see, the future path of the Milky Way and Andromeda doesn't just depend on their own gravity, it also depends on all the other galaxies nearby, tugging on them with their own gravitational pull. The biggest of these is the Large Magellanic Cloud, a dwarf galaxy that orbits the Milky Way. It's big enough to have a real effect on our galaxy's motion. If you're enjoying this journey through the cosmos and want to stay updated on the mysteries of our universe, hit that subscribe button and give this video a thumbs up. Your support helps me bring more fascinating discoveries to light. Now let's dive deeper into what scientists discovered that changed everything. In 2025, a team led by Sawala at the University of Helsinki decided to do something that hadn't been done before. They would take all the latest data from Hubble and Gaia, include the effects of smaller galaxies like the Large Magellanic Cloud, and most importantly, they would carefully account for all the uncertainties in the measurements. Then they'd run simulations, not just a few simulations, 100,000 simulations, each one slightly different, each one exploring a different possible future based on the range of uncertainty in the observations. What they found stunned the scientific community. When the results came in, Sawala and his team stared at their screens in disbelief. They had expected to confirm the collision, maybe refine the timeline a bit. Instead, they found something completely different. Out of 100,000 simulations, only about half showed a collision between the Milky Way and Andromeda in the next 10 billion years. The other half showed the galaxies either passing by each other or having such a distant encounter that they wouldn't merge at all. The probability had gone from near certainty to a coin flip. Think about what this means. For 13 years, ever since that landmark Hubble study in 2012, we've been told our galaxy's fate was sealed. Teachers taught it to students, museums built exhibits around it, scientists wrote papers assuming it would happen. And now, with better data and more careful analysis, we've discovered that we simply don't know. The universe just pulled the rug out from under one of astronomy's most famous predictions. But how is this possible? How could scientists be so wrong? Well, here's the beautiful thing. They weren't wrong. They were doing exactly what good scientists should do. They were making the best predictions they could with the data available at the time. The problem is that measuring the motion of a galaxy 2.5 million light-years away is almost impossibly difficult. Let me put this in perspective. Andromeda's motion through space has two components. There's the radial velocity, how fast it's moving toward or away from us. That's actually pretty easy to measure using the Doppler shift of light, and we've known since 1912 that Andromeda is approaching at about 100 kilometers per second. But then there's the tangential velocity, how fast it's moving sideways across our field of view. This is where things get incredibly tricky. To measure sideways motion, you need to watch something move across the sky and measure the change in position. For nearby stars, this is relatively straightforward. Gaia does it for billions of stars in our own galaxy, but Andromeda is 2.5 million light-years away. At that distance, even moving at hundreds of kilometers per second, the change in position across the sky is minuscule. We're talking about tiny fractions of an arc-second per year. An arc-second is 1/3600th of a degree. Andromeda's sideways motion is smaller than that. Hubble managed to measure it by tracking individual stars in Andromeda over several years, but the measurement came with uncertainty. The sideways velocity could be anywhere from about -125 to +125 kilometers per second. That's a huge range. And here's the critical part. Where in that range the true value falls determines whether we're headed for a collision or not. If Andromeda's sideways motion is on the lower end of that range, the galaxies are on a direct collision course. They'll slam into each other in about 4 billion years, just like the original predictions said. But if the sideways motion is on the higher end of the range, Andromeda might sweep past us, missing by hundreds of thousands of light years. We'd still have a close encounter. The gravitational effects would be dramatic, but it wouldn't be a full merger. This is where Sawala's team made their breakthrough. Previous studies had focused on the most likely value for Andromeda's motion and assumed that was what would happen. But Sawala's team realized you can't do that when you're making predictions billions of years into the future. Small uncertainties in the starting conditions get amplified over time. It's like weather forecasting. A meteorologist can predict tomorrow's weather pretty well, but predicting the weather 3 weeks from now, almost impossible because tiny uncertainties in current conditions lead to wildly different outcomes down the line. The same principle applies to galactic collisions, except we're trying to predict what happens billions of years in the future. The team ran simulations exploring every possible value within the range of uncertainty. Some simulations used the exact measurements from Hubble and Gaia. Others shifted them slightly within the margin of error. Each simulation then calculated the paths of the Milky Way and Andromeda over the next 10 billion years. The results were fascinating and diverse. In some simulations, the galaxies collided head-on in about 4 billion years, matching the classic prediction. In others, they passed within a few 100,000 light-years of each other, but didn't merge. In still others, they missed by over 1 million light-years, barely interacting at all. The universe of possible futures was far richer and more uncertain than anyone had realized. But the simulations revealed something else, something that makes this story even more interesting. It turns out the large Magellanic Cloud plays a much bigger role than anyone expected. This dwarf galaxy, visible from the southern hemisphere as a fuzzy patch in the night sky, orbits our Milky Way at a distance of about 160,000 light-years. It's the brightest satellite galaxy we have, and it's surprisingly massive for a dwarf galaxy containing perhaps 100 billion stars. If you found this discovery fascinating, you might also want to check out my video called "This is Why We Are Stuck in the Milky Way Forever," where I explore the cosmic barriers that trap us in our galactic home. It connects perfectly with what we're discussing here about galactic dynamics and the forces that shape our cosmic neighborhood. The link is in the description and on the card above. The large Magellanic Cloud isn't just orbiting peacefully, it's actually falling into the Milky Way. And when it does, probably in about 2.5 billion years, it's going to cause chaos. The collision will send ripples through our galaxy's disk. It will trigger massive bursts of star formation. And crucially, it will change our galaxy's trajectory through space. This means the Milky Way that encounters Andromeda in 4 billion years won't be quite the same Milky Way we have today. It'll be heavier, its motion will be different, and that affects whether a collision with Andromeda actually happens. Previous simulations either ignored the large Magellanic Cloud or treated it as a minor factor. Sawala's team included it properly, and that changed everything. The cloud's gravity tugs on the Milky Way, altering our path just enough that in some simulations we dodge the bullet. In others, the cloud's influence actually makes a collision more likely. It all depends on the precise timing and geometry of the encounters. There's another player in this cosmic drama that the simulations had to account for: Triangulum, also called Messier 33. This is the third largest galaxy in our local group, much smaller than the Milky Way or Andromeda, but still containing perhaps 40 billion stars. Triangulum orbits near Andromeda, and its gravitational influence affects Andromeda's path. In some simulations, Triangulum actually collides with Andromeda before Andromeda reaches us. In others, Triangulum gets flung out into intergalactic space by the encounter. The local group is a complex gravitational dance, and every partner matters. Now you might be wondering, what does all this mean for Earth, for humanity, for the future of life in our galaxy? It's a fair question, and the answer is both reassuring and mind-bending at the same time. First, let's talk about the timeline. Even in the scenarios where a collision does happen, we're looking at roughly 4 billion years from now. To put that in perspective, Earth itself is only 4.5 billion years old. 4 billion years ago, our planet was a hot, volcanic hellscape with no life whatsoever. The first single-celled organisms wouldn't appear for another 500 million years. 4 billion years is an almost incomprehensible span of time. In 4 billion years, the Sun will have changed dramatically. Right now, our star is in what astronomers call the main sequence, steadily fusing hydrogen into helium in its core. But stars don't stay the same forever. As the Sun ages, it gets gradually brighter and hotter. In about 1 billion years, maybe 1.5 billion at most, the sun will be hot enough that Earth's oceans will boil away. The runaway greenhouse effect will turn our planet into something resembling Venus, a scorched, lifeless world with surface temperatures hot enough to melt lead. By the time the Milky Way and Andromeda potentially collide, the sun will be nearing the end of its main sequence lifetime. It'll start swelling into a red giant, expanding outward until it possibly swallows the inner planets. Earth, if it still exists as a solid body, will be a charred cinder orbiting a dying star. Any life that originated on Earth will have either gone extinct billions of years earlier or migrated elsewhere in the galaxy. So in a very real sense, the question of whether our galaxies collide is not a question about Earth's fate. Earth's story will be over long before then. But what about the fate of any civilizations that might exist in our galaxy 4 billion years from now? What about the countless star systems that will be affected? This is where things get really interesting. Here's something that surprises most people. Even if the Milky Way and Andromeda do collide, the chances of any two stars actually hitting each other are almost zero. I know that sounds bizarre. We're talking about two galaxies, each containing hundreds of billions of stars smashing together. Surely there would be collisions, right? But space is mostly empty, unimaginably, incredibly empty. The Milky Way contains somewhere between 200 and 400 billion stars, spread across a disk about 100,000 light-years in diameter. If you were to scale the galaxy down so that the distance from the Sun to the nearest star, Proxima Centauri, was equivalent to the width of the United States, then stars would be about the size of grapefruits. Now imagine two collections of grapefruits, each spread across an area larger than the entire Earth, passing through each other. What are the odds that any two grapefruits would actually collide? Essentially, zero. The same principle applies to galaxies. When Andromeda and the Milky Way pass through each other, the stars will slip past one another like ghosts. Individual star systems will remain intact. Planets will keep orbiting their suns. If there are any civilizations out there, they'll have a spectacular view. Imagine looking up at the night sky and seeing not one galaxy but two, their spiral arms intertwining in a cosmic embrace, with brilliant star-forming regions lighting up where gas clouds collide. But just because stars don't collide doesn't mean nothing happens. The gravitational effects would be dramatic and transformative. As the two galaxies pass through each other, their gravity would stretch and distort the spiral arms. Stars would be flung into new orbits. Some would be tossed out into intergalactic space, becoming orphans wandering the void between galaxies. Others would plunge toward the galactic centers where supermassive black holes lurk. Oh yes, the black holes. At the heart of the Milky Way sits Sagittarius A star, a supermassive black hole with a mass of about 4 million times the Sun. Andromeda has an even larger central black hole, weighing in at around 100 million solar masses. When two galaxies merge, their central black holes eventually spiral together and combine. The resulting merger would release an enormous burst of gravitational waves, ripples in the fabric of space-time itself, powerful enough to be detected by civilizations across the universe. The gas clouds within both galaxies would collide and compress, triggering one of the most intense periods of star formation the local group has ever seen. Millions upon millions of new stars would ignite, massive blue giants that burn bright and die young, exploding as supernovae and enriching space with heavy elements. The night sky would blaze with the light of newborn stars. Over hundreds of millions of years, the two galaxies would pull apart, then fall back together for a second pass, then a third. Each time, more stars would be scattered, more gas would collapse into new stars, and the original spiral structures would become more and more distorted. Eventually, maybe after 1 billion years of this cosmic dance, the two galaxies would settle down into a single, larger entity. The beautiful spiral arms would be gone, replaced by a roughly spherical swarm of stars, an elliptical galaxy. This is the future that astronomers predicted with near certainty for over a decade. This is Milkomeda, the merger galaxy that would define our local group 5 billion years from now. Except now, we know it might not happen at all. Let's return to those simulations. Out of 100,000 runs, roughly half showed a merger. But what about the other half? What happens in those futures where the collision doesn't occur? This is where the story branches into multiple possible timelines, and each one is fascinating in its own way. In some simulations, the Milky Way and Andromeda have what astronomers call a flyby. They pass within a few 100,000 light-years of each other, close enough that their gravity significantly affects both galaxies, but not close enough to merge. Think of it like two cars on a highway passing close enough that you feel the air pressure change, but not actually touching. The gravitational interaction would still distort both galaxies. Spiral arms would be stretched. Some stars would be pulled from one galaxy into the other, but the cores would remain separate, and after the encounter, both galaxies would continue on their way, wounded but intact. In other simulations, the two galaxies miss each other by much wider margins, perhaps 1,000,000 light-years or more. At these distances, the gravitational effects would be minimal. Both galaxies would continue their separate journeys through the expanding universe, gradually drifting apart as the space between them grows. Future astronomers in both galaxies would watch their neighbor recede into the distance, eventually becoming just another distant island of stars in an increasingly empty sky. This brings us to one of the most profound aspects of this discovery: the role of uncertainty in our understanding of the cosmos. We live in an age where science can seem almost magical. We've sent robots to Mars, detected gravitational waves from colliding black holes billions of light-years away, and photographed the shadow of a black hole at the center of a distant galaxy. It's easy to think we have everything figured out, that science has given us certainty about the universe. But the truth is more nuanced and, in many ways, more beautiful. Science isn't about achieving perfect certainty. It's about narrowing down the range of possibilities, about understanding what we know and being honest about what we don't. The story of the Andromeda collision is a perfect example of this. For years, the predictions seemed certain because we focused on the most likely outcome. But when we carefully examined the full range of possibilities allowed by our measurements, we discovered that certainty was an illusion. This is actually how science should work. When Sawala and his colleagues published their findings in Nature Astronomy in June of 2025, they weren't saying the previous scientists were wrong. They were building on that earlier work, using better data and more sophisticated analysis to get a clearer picture. The Hubble measurements from 2012 were groundbreaking and correct within their margin of error. But margins of error matter, especially when you're predicting events billions of years in the future. The new study used data from Gaia, which has revolutionized our understanding of stellar motions in ways that weren't possible before. Launched by the European Space Agency, Gaia has measured the positions, distances, and motions of nearly 2 billion stars with extraordinary precision. By tracking how stars in Andromeda move relative to the background universe, Gaia provided independent confirmation of Andromeda's motion, and more importantly, it helped narrow down the uncertainties. But even with Gaia's incredible precision, uncertainty remains. The measurements are better, the error bars are smaller, but they're still there. And that's okay. That's not a failure of science. It's a reminder of the scale of what we're trying to accomplish. We're standing on a planet orbiting an ordinary star in the outer suburbs of a galaxy containing hundreds of billions of stars, trying to predict what will happen when our galaxy encounters another galaxy 2.5 million light-years away, 4 billion years in the future. The fact that we can narrow it down to a 50-50 chance is actually astounding. Let's zoom out for a moment and consider the bigger picture. The Milky Way and Andromeda are part of the local group, but the local group is just one tiny corner of a much vaster universe. Our local group is part of the Virgo supercluster, a massive collection of galaxies spanning over 100 million light-years, and the Virgo supercluster is itself just one lobe of an even larger structure called Laniakea, which contains about 100,000 galaxies. On these vast scales, the dance between the Milky Way and Andromeda is just one small interaction among countless others. Throughout the universe, galaxies are colliding, merging, and transforming all the time. The Hubble Space Telescope and other observatories have captured images of galaxy collisions at various stages. Some show galaxies just beginning to interact, their spiral arms reaching out toward each other like cosmic fingers. Others show galaxies in the middle of violent mergers with stars and gas flung across millions of light-years. Still others show the final products, elliptical galaxies, their spiral structures destroyed, their star formation exhausted, settling into a quiet old age. These observations tell us that galaxy mergers are a normal part of cosmic evolution. In the early universe, galaxies collided and merged frequently, building up larger galaxies over time. Our own Milky Way has consumed dozens of smaller galaxies throughout its history. In fact, some of the stars in our galactic halo, the spherical cloud of old stars surrounding the main disk, are refugees from dwarf galaxies that our Milky Way devoured billions of years ago. The large Magellanic cloud that we mentioned earlier is probably going to meet the same fate in a few billion years. So whether or not the Milky Way and Andromeda collide, our galaxy is not static. It's constantly evolving, constantly changing. The Milky Way of today is not the same galaxy it was 10 billion years ago, and it won't be the same galaxy 10 billion years from now. Stars are born and die. Gas clouds collapse and disperse. Smaller galaxies are absorbed. The spiral arms we see today are temporary structures, waves of star formation moving through the disk like ripples on a pond. This brings us to an interesting question. Why do we care so much about whether the collision happens or not? After all, as we've established, it won't affect Earth. It won't affect the Sun. It probably won't even significantly affect individual star systems. Stars will simply find themselves in new orbits around a restructured galactic center. So why does this prediction matter? I think it matters for several reasons. First, it's a test of our understanding of gravity and galactic dynamics. If we can accurately predict the motion of galaxies billions of years into the future, it demonstrates that we truly understand the fundamental forces governing the universe. The fact that our predictions have now become less certain isn't a failure, it's a refinement. We're learning to be more honest about the limits of our knowledge. Second, studying galactic interactions helps us understand how galaxies evolve over cosmic time. The universe is about 13.8 billion years old. In the early universe, galaxies were smaller and collisions were common. Today, in our cosmic neighborhood, major collisions are relatively rare. But in the future, as the universe continues to expand and galaxies drift apart, collisions will become even rarer. Understanding how and when galaxies merge helps us piece together the story of how structure formed in the universe. Third, and perhaps most importantly, it connects us to the grandest story there is, the story of the cosmos itself. We are not separate from the universe observing it from the outside, we are part of it. The atoms in your body were forged in the cores of dying stars billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created by nuclear fusion in stellar furnaces and scattered across space by supernova explosions. When we study the fate of galaxies, we're studying the environment that made us possible. Carl Sagan famously said that we are made of star stuff. He was right. But it goes deeper than that. We are made of galaxy stuff. The heavy elements in our bodies were created not just in any stars, but in stars within galaxies, recycled through multiple generations of stellar birth and death. If the Milky Way had never collided with and absorbed smaller galaxies in its past, it might not have had enough heavy elements to form rocky planets like Earth. In a very real sense, previous galactic collisions made us possible. This perspective helps us appreciate why astronomers spend so much time studying events that won't happen for billions of years. It's not just academic curiosity, though curiosity is a beautiful thing in itself. It's about understanding our place in the cosmic story, about seeing the connections between the largest structures in the universe and the smallest details of our existence. Now let's talk about the technology that made this discovery possible, because the story of the Andromeda collision is also a story about human ingenuity and the relentless improvement of our tools for exploring the universe. The Hubble Space Telescope, launched in 1990, has been humanity's eye on the cosmos for over 3 decades. Despite its age and the challenges of operating in space, Hubble continues to make groundbreaking discoveries. The measurements Hubble made of Andromeda's motion required some of the most precise observations ever attempted. Astronomers had to track individual stars in Andromeda over several years, measuring changes in position so tiny that they're almost at the limit of what's physically possible. Think about trying to measure the thickness of a human hair from a mile away, and you'll get a sense of the challenge. Hubble managed it by repeatedly photographing the same regions of Andromeda, then carefully comparing images taken years apart to see how stars had moved. But Hubble was designed in the 1980s and launched in the 90s. Technology has advanced enormously since then. Enter Gaia, which represents a completely different approach to mapping the cosmos. Instead of focusing on specific targets like Hubble does, Gaia continuously scans the entire sky, measuring the positions and motions of everything it can see. Over its mission lifetime, which began in 2013, Gaia has observed some stars hundreds of times, building up extraordinarily precise measurements of their motions. Gaia's contribution to understanding the Andromeda encounter goes beyond just measuring Andromeda itself. By mapping the motions of stars throughout the local group, Gaia has helped astronomers understand the gravitational environment in which both galaxies exist. Remember, it's not just about the Milky Way and Andromeda. The large Magellanic Cloud, the small Magellanic Cloud, Triangulum, and dozens of smaller dwarf galaxies all contribute to the gravitational dance. Gaia has helped us measure the masses and motions of these smaller players, which turns out to be crucial for predicting what happens next. The combination of Hubble's targeted precision and Gaia's comprehensive mapping has given us the best data we've ever had about the local group. But even with these remarkable instruments, we're still dealing with significant uncertainties. This points to an important truth about astronomy. No matter how good our telescopes get, some questions remain difficult to answer because of the sheer scale and complexity of what we're studying. Let's consider what would be needed to definitively answer the question of whether the collision will happen. We'd need to measure Andromeda's tangential velocity to much higher precision than current technology allows. We'd need better measurements of the masses of all the galaxies in the local group, including the dark matter halos that surround them, and we'd need to account for smaller effects that current simulations might be neglecting, like the influence of dark energy on the expansion of space, or the cumulative gravitational pull of galaxies beyond the local group. Dark matter deserves special attention here because it plays an enormous role in galactic dynamics. When astronomers measure the mass of a galaxy, they're not just counting up all the stars and gas they can see. Most of a galaxy's mass is actually invisible, made up of dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. We only know it exists because of its gravitational effects. Both the Milky Way and Andromeda are embedded in massive halos of dark matter that extend far beyond their visible edges. These dark matter halos contain perhaps 10 times as much mass as all the visible stars and gas combined. When two galaxies approach each other, their dark matter halos start interacting long before the visible parts of the galaxies get close. This interaction acts like a cosmic brake, slowing down the galaxy's relative motion through a process called dynamical friction. The strength of this braking effect depends on the exact distribution and amount of dark matter in each galaxy's halo. If the halos are more massive or more extended than we think, dynamical friction will be stronger and a collision becomes more likely. If the halos are less massive or more compact, friction is weaker and the galaxies might pass by each other. Our uncertainty about dark matter's properties translates directly into uncertainty about the collision. Current estimates suggest the Milky Way has a total mass, including dark matter, of about 1 trillion solar masses. Andromeda is thought to be somewhat more massive, maybe 1.2 to 1.5 trillion solar masses. But these are estimates with substantial error bars. Future observations, perhaps from next-generation telescopes, might narrow down these masses more precisely. Each improvement in our measurements shifts the odds slightly one way or the other. There's another factor that makes long-term predictions challenging: the three-body problem. You might have heard of this in the context of science fiction or physics discussions. The three-body problem refers to the fact that when you have three objects interacting gravitationally, their motions become chaotic and unpredictable over long timescales. With two objects like the Earth and the Moon, you can predict their orbits essentially forever. But add a third object, and the system becomes much more complex. Now, the local group doesn't just have three bodies. It has hundreds if you count all the dwarf galaxies. This creates what mathematicians call a chaotic system. Small changes in initial conditions can lead to dramatically different outcomes over time. This is why Sawala's team had to run 100,000 simulations. They were essentially exploring the full space of possible futures, seeing how different starting conditions, all consistent with current observations, led to different outcomes. This inherent unpredictability isn't a flaw in our understanding, it's a fundamental property of the system itself. Even if we had perfect measurements of every galaxy's position and velocity today, we still couldn't predict with certainty what would happen 4 billion years from now. The system is simply too complex, too sensitive to initial conditions. The best we can do is calculate probabilities, map out the range of possible futures, and acknowledge that the universe doesn't follow a predetermined script. I find this deeply beautiful. It means the universe has genuine openness, genuine possibility. The future isn't written. Multiple timelines exist as real potentials, and which one unfolds depends on countless small factors. The flutter of a galaxy's motion today, a tiny perturbation from a passing dwarf galaxy, could determine whether two great galaxies merge or miss each other billions of years from now. This uncertainty connects to a broader question that has fascinated philosophers and scientists for centuries. Is the universe deterministic or probabilistic? In other words, if you knew the exact state of everything in the universe at one moment, could you calculate everything that would happen afterward? Classical physics, the physics of Newton and Einstein's gravity, says yes. But quantum mechanics says no, introducing fundamental randomness at the smallest scales. And chaos theory says that even in deterministic systems, practical prediction becomes impossible over long timescales. The story of the Andromeda collision touches on all three of these ideas. At the quantum level, random fluctuations are constantly occurring, though they're too small to affect galactic motions. At the classical level, Newton's laws and Einstein's general relativity govern how galaxies move, and these are deterministic equations. But at the practical level, chaos and complexity mean we can't actually predict the outcome with certainty, even though the laws themselves are deterministic. This is one of the reasons I love astronomy and cosmology. These fields force us to grapple with deep questions about knowledge, prediction, and the nature of reality itself. They remind us that science isn't just a collection of facts. It's a way of thinking, a method for asking questions and refining our understanding of the world. Let me share something that might shift your perspective even further. While we've been talking about whether the Milky Way and Andromeda will collide, there's a larger process happening that dwarfs this local drama: the expansion of the universe. Ever since the Big Bang, about 13.8 billion years ago, space itself has been expanding, carrying galaxies apart from each other. Edwin Hubble discovered this in 1929, and it revolutionized our understanding of the cosmos. Here's the fascinating part. The Milky Way and Andromeda are close enough that their mutual gravity overcomes the expansion of space. That's why Andromeda is moving toward us rather than away. But beyond the local group, expansion dominates. Distant galaxy clusters are receding from us, and the farther away they are, the faster they're moving. Eventually, at extreme distances, galaxies are receding faster than the speed of light. Not because they're moving through space that fast, but because space itself is expanding. This expansion is accelerating, driven by something called dark energy, which makes up about 68% of the universe's total energy content. We don't really know what dark energy is, we just know it causes the expansion to speed up over time. As billions of years pass, this accelerating expansion will eventually pull apart even gravitationally bound structures. Galaxy clusters will be torn apart. Individual galaxies will become isolated islands in an increasingly empty universe. But that's far in the future. For now, on the timescale of billions of years, the local group remains bound together. Whether the Milky Way and Andromeda merge or not, they're not being pulled apart by cosmic expansion. They're locked in a gravitational embrace that transcends the overall expansion of the universe. In a cosmos that's constantly growing and diluting, the local group is a pocket of stability, at least for now. This makes our situation somewhat special. In the far future, perhaps hundreds of billions of years from now, any civilizations that exist will look out and see essentially nothing beyond their own galaxy. The expansion of space will have carried everything else beyond the observable horizon. They'll have no way to know that other galaxies exist or ever existed. The evidence of the Big Bang itself will have faded. Future astronomers will face a much lonelier, more mysterious universe than we do. We live in a privileged time, cosmologically speaking. We can see the cosmic microwave background, the afterglow of the Big Bang. We can observe distant galaxies and map the large-scale structure of the universe. We can piece together the history of cosmic evolution from the first moments after the Big Bang to the present day. Future civilizations won't have this luxury. In a sense, we're living in the golden age of cosmology, when the universe is old enough to have formed complex structures like galaxies and planets and life, but young enough that the evidence of its history is still visible. The question of whether the Milky Way and Andromeda collide fits into this bigger picture. If they merge, the resulting elliptical galaxy will be the dominant structure in our local group for the rest of cosmic time. Any civilizations that arise within it will live in a galaxy shaped by that ancient collision. If they don't merge, both galaxies will continue their separate evolution, perhaps eventually drifting apart as dark energy dominates even on these scales. Either way, the local group represents one of countless experiments in galaxy evolution happening throughout the universe. Each cluster, each group of galaxies, has its own unique history and future. Some will merge into giant ellipticals. Others will remain as collections of smaller galaxies. By studying our own local group, we learn about the range of possibilities that exist everywhere. Now let's talk about what this discovery means for the scientific process itself. When the news broke in June 2025 that the Andromeda collision was no longer certain, it made headlines around the world. Some headlines were sensationalized, claiming that scientists had been completely wrong or that the previous prediction was a mistake. But that's not really what happened, and it's important to understand why. Science works by making the best predictions possible with available data, then constantly testing and refining those predictions as new data comes in. The 2012 Hubble study was excellent science. It made careful measurements, acknowledged uncertainties, and drew reasonable conclusions. The conclusion was that a collision was very likely, and given the data available at the time, that was the right conclusion to draw. What changed wasn't that someone found an error in the old calculations. What changed was that new data became available from Gaia and from better measurements of galaxy masses, and scientists developed more sophisticated ways of accounting for uncertainty. When Sawala's team incorporated all of this, they got a different answer. Not because the old answer was wrong, but because science had progressed. This is exactly how science should work. It's self-correcting. When new evidence comes in, we update our understanding. We don't cling to old ideas out of pride or tradition. We follow the evidence wherever it leads, even if it means revising predictions that seemed certain for years. The public sometimes misunderstands this process. When scientific consensus changes, some people interpret it as science being unreliable or scientists not knowing what they're talking about. But it's actually the opposite. The ability to change our minds in light of new evidence is science's greatest strength, not a weakness. It's what distinguishes science from dogma. Think about how different this is from other ways of understanding the world. In many belief systems, ancient texts or traditional teachings are treated as unchangeable truth. Questioning or revising them is seen as heresy, but in science, questioning and revising are essential. Every scientific theory, no matter how well established, is always open to challenge by new evidence. That's not a bug, it's a feature. It's what allows science to make progress. The Andromeda collision story also illustrates another important aspect of science, the difference between precision and accuracy. Precision refers to how exact your measurements are, how many decimal places you can report. Accuracy refers to how close your measurements are to the true value. You can have very precise measurements that are not accurate if there's some systematic error you haven't accounted for. And you can have accurate measurements that aren't very precise if your error bars are large. The challenge with measuring Andromeda's motion is that we need both precision and accuracy at levels that push the boundaries of what's possible. Hubble and Gaia have given us unprecedented precision, but the accuracy is limited by factors like how well we understand the reference frame we're measuring against, how well we can separate Andromeda's motion from the motion of stars within it, and how well we can account for gravitational effects from other nearby objects. Each generation of telescopes improves both precision and accuracy. The James Webb Space Telescope, which launched in December 2021, has capabilities that exceed Hubble in many ways. Webb could potentially contribute to refining measurements of the local group's dynamics, though its primary mission focuses on other questions like the formation of the first galaxies and the atmospheres of exoplanets. Future space missions might be specifically designed to nail down the motions of nearby galaxies with even greater precision. Imagine a successor to Gaia, optimized for measuring motions not just within our galaxy, but in neighboring galaxies as well. Such a mission could reduce the uncertainties enough that we might move from a 50-50 probability to something more definitive. But that mission doesn't exist yet. For now, we live with uncertainty, and that's okay. Let's shift gears and talk about what we can learn from simulations like the ones Sawala's team ran. Computer simulations have become one of the most powerful tools in modern astronomy. We can't run experiments on galaxies. We can't move them around in a laboratory and see what happens, but we can build mathematical models that capture the physics of gravity, gas dynamics, star formation, and dark matter, then let those models evolve forward in time. The simulations that predicted the possible futures of the Milky Way and Andromeda are incredibly sophisticated. They start with the current positions and velocities of all the major galaxies in the local group, including the uncertainties in those measurements. They include the dark matter halos surrounding each galaxy. They incorporate the effects of gas dynamics and star formation. Then they let the simulation run forward, calculating how gravity pulls everything around for billions of years of simulated time. Running 100,000 such simulations required enormous computing power. Modern supercomputers can perform trillions of calculations per second, but even so, simulating the evolution of multiple galaxies over billions of years is computationally expensive. Each simulation might take hours or days to complete. Multiply that by 100,000 and you're talking about a massive computational effort. But the payoff is worth it. By running so many simulations, the researchers could map out the full probability distribution of possible futures. They could see not just what's most likely to happen, but also what the range of possibilities looks like. Some outcomes are common, appearing in many simulations. Others are rare, showing up in only a few runs. This probabilistic approach gives us a much richer understanding than simply trying to predict a single outcome. Interestingly, the simulations also revealed some surprises beyond just the collision probability. For instance, in some of the scenarios where the Milky Way and Andromeda don't merge, the Large Magellanic Cloud plays a crucial role. Its collision with the Milky Way can actually change our galaxy's trajectory enough to avoid Andromeda entirely. In a sense, the Large Magellanic Cloud might save us from a collision by colliding with us first. The universe has a sense of irony. In other simulations, Triangulum becomes the wild card. Depending on its exact orbit around Andromeda, Triangulum can either facilitate a merger by gravitationally nudging the two large galaxies together, or it can disrupt the interaction by pulling Andromeda slightly off course. With three or more large bodies interacting, the possibilities multiply dramatically. The simulations also showed that even in scenarios where no major collision occurs, the local group doesn't remain static. Galaxies orbit around their common center of mass, which itself is moving through space. Smaller dwarf galaxies get pulled and pushed by the gravity of their larger neighbors. Some get stripped of their gas and stars, gradually fading away. Others fall into the larger galaxies and are absorbed. The local group is a dynamic, ever-changing system. This dynamic nature extends to our own Milky Way. Even without a collision with Andromeda, our galaxy is constantly evolving. Stars are born in the spiral arms at a rate of about 1 to 2 solar masses per year. That might not sound like much, but over billions of years, it adds up. At the same time, stars are dying. Low-mass stars like our Sun will eventually swell into red giants, shed their outer layers, and fade as white dwarfs. High-mass stars will explode as supernovae, leaving behind neutron stars or black holes. The spiral arms themselves are not permanent structures. They're actually density waves, regions where stars and gas temporarily bunch up as they orbit the galactic center. Imagine cars bunching up in a traffic jam on a highway. The jam moves along the road, but individual cars enter it, slow down, then leave, and speed up again. Similarly, stars pass through the spiral arms during their orbits. The arms persist, but they're not made of the same stars all the time. Over billions of years, the Milky Way's spiral structure might change. The arms might become more or less prominent. The bar at the center of our galaxy, an elongated structure of stars that rotates as a unit, might grow stronger or weaker. These changes depend on complex interactions between stars, gas, and dark matter that we're still working to understand fully. If the Large Magellanic Cloud collides with us in 2.5 billion years, as expected, that will dramatically affect the Milky Way's structure. The collision will send ripples through the galactic disk, potentially triggering intense bursts of star formation. It might even disrupt the spiral arms temporarily. By the time we potentially encounter Andromeda 4 billion years from now, we'll be a somewhat different galaxy than we are today. All of this raises a fascinating philosophical question. What does it mean for a galaxy to have an identity? If the Milky Way absorbs the Large Magellanic Cloud, is it still the same galaxy? If it merges with Andromeda to form Milkomeda, does the Milky Way cease to exist, or does it continue in a new form? These might seem like semantic questions, but they touch on something deeper about how we understand continuity and change. Human beings have grappled with similar questions for millennia. The ancient Greek philosopher Heraclitus said you can never step in the same river twice because the water is always flowing and changing, yet we still call it the same river. Your body replaces most of its cells every 7 to 10 years, yet you remain the same person. Galaxies, like rivers and people, are processes rather than static things. They persist through time while constantly changing. This perspective helps us appreciate the cosmic story in a new way. We're not just observers watching a fixed universe unfold according to a predetermined script. We're participants in an ongoing process of change and transformation. The atoms in your body have been parts of many different structures throughout cosmic history. They were forged in stellar cores, scattered by supernovae, incorporated into gas clouds, condensed into new stars and planets, and eventually became part of you. Billions of years from now, those same atoms will be part of something else entirely. Whether the Milky Way and Andromeda merge or not, the story continues. Matter and energy transform, but they don't disappear. The universe is endlessly creative, constantly generating new structures from old materials. Every ending is also a beginning. Let's consider what happens in the far, far future, beyond even the possible Andromeda collision. Cosmologists have traced the universe's evolution forward trillions upon trillions of years, long after the last stars have burned out. In this distant future, stellar remnants like white dwarfs, neutron stars, and black holes will be all that remain of the glorious galaxies we see today. Even these remnants won't last forever. Protons themselves might eventually decay, though we're not certain about this. If they do, even the white dwarfs will slowly evaporate into radiation over timescales so long that billions of years seems like the blink of an eye. Black holes will be the last structures to persist, slowly evaporating through Hawking radiation, a quantum process that causes them to leak energy over incomprehensibly long timescales. The largest supermassive black holes, like the ones at the centers of galaxies, will take something like 10 to the 100 years to evaporate. That's 1 followed by 100 zeros, a number so large it's essentially meaningless to human intuition. The current age of the universe, 13.8 billion years, is nothing compared to these timescales. We live in the early morning of cosmic time. But we're getting ahead of ourselves. Before we worry about the heat death of the universe in the unimaginably distant future, we should appreciate the present. Right now, at this moment in cosmic history, the universe is filled with beauty and complexity. Galaxies spiral majestically through space, stars shine in countless colors, planets orbit in intricate dances, and on at least one planet, conscious beings look up at the sky and wonder about their place in it all. This capacity for wonder is perhaps our most precious gift. We are made of atoms that were forged in stars, arranged by the blind processes of physics and chemistry into patterns complex enough to contemplate their own existence. We can look at Andromeda, that smudge of light in the night sky, and understand that it's an island of hundreds of billions of stars, each potentially with planets of its own. We can calculate its motion, predict its future, and feel a sense of connection to it across the vast gulf of space. The discovery that the Andromeda collision is less certain than we thought doesn't diminish this wonder. If anything, it enhances it. The future is genuinely open. Multiple possibilities exist simultaneously, each as real as the others until time itself selects which one will unfold. We live in a universe with true uncertainty, true possibility, true creativity. This openness extends beyond astronomy. Think about your own life. You make decisions every day, small and large, that shape your future. Some outcomes are more probable than others, but none are certain. You exist in a space of possibilities, and your choices help determine which possibility becomes reality. In a strange way, the uncertainty about galactic collisions billions of years from now mirrors the uncertainty in your own life. Of course, there's a crucial difference. You have agency. You can make choices that influence your future. Galaxies don't choose their paths, they follow the laws of physics. But the uncertainty is real in both cases. Physics is deterministic at the classical level, but complexity and chaos mean that prediction remains impossible beyond certain limits. Your brain is a physical system subject to the same laws, yet somehow it generates the experience of choice and the ability to shape your own story. These mysteries connect in surprising ways. The same quantum fluctuations that seeded the formation of galaxies in the early universe also play a role in neural processes in your brain. The same gravitational forces that will determine whether galaxies collide also keep you anchored to the Earth's surface. The same laws of thermodynamics that govern stellar evolution also govern the metabolism that keeps you alive. Everything is connected. This is why I find astronomy so compelling. It's not just about distant objects in the sky. It's about understanding our connection to the cosmos, seeing ourselves as part of an unfolding story that began with the Big Bang and will continue for unimaginable spans of time. Every atom in your body, every moment of your existence, is a chapter in this grand narrative. The question of whether the Milky Way and Andromeda will collide is really a question about how this particular chapter of the cosmic story will unfold. It's a question about the future of hundreds of billions of stars, any of which might have planets, some of which might harbor life. It's a question about the long-term evolution of structure in an expanding universe. And it's a question that reminds us of the limits of our knowledge and the vastness of what remains to be discovered. So where do we go from here? What's the next step in this scientific journey? The story of the Andromeda collision is far from over. In fact, it's entering an exciting new phase where better observations and more sophisticated models will continue to refine our understanding. Several upcoming and proposed missions could contribute to resolving the uncertainty. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will have a field of view 100 times larger than Hubble's. While its primary mission focuses on dark energy and exoplanets, it could also contribute to mapping stellar motions in nearby galaxies. The European Space Agency is planning a successor to Gaia that could extend precision astrometry to even greater distances. Ground-based telescopes are also becoming more powerful. The extremely large telescope currently under construction in Chile will have a mirror 40 meters in diameter when completed. That's almost 5 times larger than any existing optical telescope. With adaptive optics to correct for atmospheric distortion, it will be able to resolve individual stars in galaxies far beyond the local group. Such observations could help us better understand galaxy dynamics and test our models against a wider range of examples. But technology is only part of the story. Theoretical advances matter just as much. Astronomers are developing increasingly sophisticated simulations that include more physics, more detail, and more careful treatment of uncertainties. Machine learning and artificial intelligence are being applied to analyze vast data sets and identify patterns that human researchers might miss. These computational tools are transforming how we do astronomy. There's also growing interest in multi-messenger astronomy, where we combine observations across different types of signals. We're used to observing the universe with light across all wavelengths from radio waves to gamma rays, but we can also observe gravitational waves, ripples in space-time caused by accelerating masses. The LIGO and Virgo observatories have detected gravitational waves from colliding black holes and neutron stars. Future detectors, like the planned LISA space-based observatory, will be sensitive to lower-frequency gravitational waves, potentially including signals from supermassive black holes orbiting each other in merging galaxies. If the Milky Way and Andromeda do eventually merge, the coalescence of their central black holes billions of years from now will produce gravitational waves powerful enough to detect across the universe. Of course, we won't be around to observe it directly, but the principles we're learning today by studying other galaxy mergers will apply to our own potential future. This brings me to something I think is profoundly important: the long-term perspective that astronomy gives us. In our daily lives, we worry about next week, next month, maybe the next few years. Political leaders plan in terms of election cycles, maybe a decade or two at most. But astronomy forces us to think in terms of millions, billions, even trillions of years. This perspective is humbling and liberating at the same time. Humbling because it reminds us how brief our individual lives are, how tiny we are in the cosmic scale. Everything we worry about, all our struggles and triumphs, plays out on a planet orbiting an ordinary star in the suburbs of a galaxy that might or might not collide with its neighbor billions of years from now. In the grand scheme of things, we're almost infinitesimally small and brief, but liberating because this perspective also shows us that we're part of something vastly larger than ourselves. We're not separate from the universe, looking at it from outside. We're made of the same stuff as stars and galaxies. We're the universe experiencing itself, becoming aware of itself, asking questions about itself. Every time you look up at the night sky and feel a sense of wonder, that's the cosmos contemplating its own existence through you. This dual sense of insignificance and significance is, I think, the appropriate response to our cosmic situation. We're tiny, yes, but we're also extraordinary. The universe is 13.8 billion years old and incomprehensibly vast, yet somehow, against all odds, it has arranged itself into patterns capable of thought, feeling, and wonder. You are one of those patterns. You are the cosmos made conscious. The question of whether two galaxies will collide 4 billion years from now might seem abstract and distant from your everyday concerns. And in one sense, it is. Nothing about this prediction will affect your life, your choices, or your immediate future. But in another sense, it's deeply relevant because it connects you to the larger story of cosmic evolution. It reminds you that you live in a dynamic, changing universe, full of beauty and mystery and possibility. I believe this perspective has practical value, even if it doesn't help you pay your bills or solve your immediate problems. It gives context. It reminds you what's truly important. When you're stressed about trivial matters, remembering the cosmic scale can help you let go. When you're feeling lost or purposeless, remembering that you're made of stardust and connected to everything can provide a sense of meaning. And it encourages curiosity, which I believe is one of the most valuable human traits. Curious people ask questions, they seek understanding, they're open to new ideas and willing to change their minds when presented with evidence. The world needs more curiosity, more willingness to wonder, more openness to the possibility that what we think we know might not be quite right. The story of the Andromeda collision embodies this spirit of curiosity and open-mindedness. For 13 years, the scientific consensus was that the collision would definitely happen. Then better data and more careful analysis revealed that we can't be certain after all. This isn't a failure of science, it's science working exactly as it should. It's the willingness to question, to refine, to say, we were too confident before and here's what we actually know now. Imagine if all areas of human endeavor operated with this level of intellectual humility. Imagine if political leaders said, based on the best evidence available, we think this policy will work, but there's significant uncertainty and will adjust course if new evidence suggests we were wrong. Imagine if we all approached our beliefs and opinions with the understanding that they're provisional, subject to revision in light of new information. This doesn't mean abandoning all conviction or believing that all opinions are equally valid. Some ideas are well supported by evidence, while others are not. The Earth is round, not flat. Vaccines save lives. The universe is billions of years old, not thousands. These are facts supported by overwhelming evidence. But even our best supported theories are always open to refinement and improvement. That's what makes science so powerful. The Andromeda collision story is a perfect example. The basic facts are solid. Andromeda is approaching us at about 110 kilometers per second. It's about 2.5 million light-years away. Both galaxies are massive, with hundreds of billions of stars and enormous dark matter halos. These facts aren't in dispute. What's uncertain is exactly what will happen when you extrapolate these facts billions of years into the future through a complex, chaotic system. This distinction between what we know and what we're uncertain about is crucial. It's the difference between healthy skepticism and cynical rejection of all expertise. Healthy skepticism says, show me the evidence, explain your reasoning, and I'll evaluate it critically. Cynical rejection says, you can't really know anything, so all claims are equally dubious. The first leads to progress, the second leads to paralysis. In the case of the Andromeda collision, we can be confident about the present-day measurements while remaining uncertain about the long-term prediction. That's intellectually honest. It's living with ambiguity while still pursuing knowledge. And it's a valuable life skill that extends far beyond astronomy. As we wrap up this cosmic journey, let me leave you with a few final thoughts. The universe is vast, ancient, and filled with wonders beyond imagination. We're privileged to live in a time when we can observe and understand it with unprecedented clarity. The telescopes we've built, the theories we've developed, and the simulations we've run give us a window into the cosmos that our ancestors couldn't have dreamed of. Whether the Milky Way and Andromeda collide or not, the show will be spectacular. If they merge, future civilizations, should any exist, will witness one of the most dramatic events in galactic evolution. A billion-year ballet of stars and gas clouds culminating in the birth of a new galaxy from the fusion of two ancient ones. If they don't collide, both galaxies will continue their separate journeys through the expanding universe, each evolving according to its own internal dynamics and external influences. Either way, the story continues. The cosmic dance goes on. Stars are born and die, planets form and are destroyed. And somewhere, perhaps on many worlds throughout the universe, conscious beings look up at the sky and wonder about their place in it all, just as we do. This sense of wonder, this capacity to ask questions about the universe and our place in it, might be our most remarkable characteristic. We're not the fastest or strongest species, we don't have the keenest senses, but we have curiosity, imagination, and the ability to use science and reason to understand things far beyond our direct experience. We can look at a fuzzy patch of light in the night sky and know that it's a galaxy containing hundreds of billions of stars hurtling through space on a trajectory we can measure and predict. That's extraordinary, that's worth celebrating, and that's worth continuing to pursue even when the questions we ask have answers that won't affect our immediate lives. Understanding the cosmos is valuable in itself, regardless of practical applications. It enriches us. It connects us to something larger. It reminds us of the beauty and mystery and vastness of existence. So the next time you look up at the night sky and see Andromeda, that faint smudge in the constellation of the same name, visible to the naked eye on a dark, clear night, take a moment to appreciate what you're seeing. You're looking at light that left that galaxy 2.5 million years ago, when our ancestors were just beginning to use stone tools. You're seeing hundreds of billions of suns, worlds beyond counting, all bound together by gravity into a structure so vast it defies imagination. And remember that this distant galaxy might, billions of years from now, merge with our own, or it might not. The future is open. The universe still has surprises in store, and we're fortunate enough to be conscious beings capable of wondering about it all. The cosmos is calling to us, inviting us to explore, to question, to understand. Whether we're contemplating galactic collisions billions of years in the future, or the challenges and opportunities in our own lives, the same principle applies. Stay curious, remain open to new evidence, and never stop wondering. The universe is vast and full of mysteries, but with science as our guide, curiosity as our compass, and wonder as our constant companion, we can continue to unravel those mysteries, one question at a time. The story of whether the Milky Way and Andromeda will collide is just one chapter in the grand narrative of cosmic evolution. It's a chapter we're still writing, a question we're still answering. And that, ultimately, is what makes science so thrilling. It's not a completed book of unchanging facts. It's an ongoing investigation, a continuous quest for understanding. Every answer leads to new questions. Every discovery opens new horizons. The journey never ends, and that's exactly as it should be. If you're fascinated by the scales of space and our place in the cosmos, I invite you to watch my video called The Absolute Limit of Human Travel Through Space. It's at the left side of the screen. In that video, we explore just how far humanity could ever hope to travel, given the constraints of physics, the expansion of the universe, and the limits of technology. See you there.